Hey there, Calc 2 folks, back here with another lecture in our introduction to vectors in 2 and 3-dimensional space, where I want to continue with that idea of vector operations, where we add to that list of the operations that we had seen in the previous sections of material. Right, in the previous sections we had talked about vector addition, vector subtraction, and what we call scalar multiplication of a vector. Right? What we did not introduce in terms of operations were what we might think of as products. Right? There are two additional vector operations encountered in the study of vectors, right? Illustrating what we call vector products, right? Or really, I should say the product for the case, illustrating the cases for, we might say here, let's be careful there, products of vectors. And that is the case for what we call a dot product and the case for what we call a cross product. The dot product being a case that produces a scalar result for the product, and the cross product being a case that produces a vector result for the product. We call those the scalar product and the vector product respectively. So I wanted to be careful how I stated that up above. Now, what this section is going to focus in on is that scalar product known here as the dot product, right? Which does have the following definition to it. Right? If we let u and v be two non-zero vectors, right? Two vectors that are not composed entirely of zeros, right? The dot product of u with the value of v is going to be a scalar value, right? Given by this quantity seen here. It is denoted as the dot product of u with v. We might say here, let's go ahead and get the notation also highlighted here. Denoted as vector u dotted with vector v, right, is the scalar value given by this quantity seen down below here. It is u dot v, which equals this product of these three values. The magnitude of u multiplied by the magnitude of v times what would be the cosine of theta. Theta being the smallest angle formed between vectors u and v when they are placed in standard position. Theta being some angle measurement in that interval from 0 to pi, right? If it's going to be one of the smaller angles formed between u and v in standard position. This is the value that we define as the scalar product known as the dot product. Right? It is a value that is dependent upon it is a scalar value, we should say, dependent upon the magnitudes of u and v and the angle measurement theta that forms between these vectors when they're placed in standard position. Right? One thing we can note, what dot products allow us to explore is the angle between two vectors, and we note if the dot product of two values equals 0, then what is going to be true is that theta, if those two vectors, u and v, are non-zero vectors and their dot product equals 0, then what must be true is that this angle measurement theta seen in the cosine here must be equivalent to pi over 2. Right? The only way this whole product of three factors would be equal to 0 if these two magnitudes are not 0 would be when the cosine of theta equals 0, and if theta is an angle measurement between 0 and pi, theta will end up being 0 when it's equal to pi over 2. So pi over 2 is going to be the angle measurement that forms between u and v that is said to be an orthogonal measurement between u and v, right? Where u and v are orthogonal to each other. And what you will see is if u and v are orthogonal to each other in the space in which you're calculating their dot product, their dot products will equal 0 in value. All right, so that is also pointed out there in that definition. Now, it's very unlikely that if you're given two vectors that you will know the angle measurement between those two vectors. What you'll more likely have is just those two vectors themselves. And how you're going to go about calculating the dot product in either 2 or 3-dimensional space is you're going to have to rely on the following theorem here. Now, this theorem in 2-dimensional space says that if we have the 2-dimensional vector u equal to u1 comma u2 with its components, and v equal to the vector v1 comma v2 with its components, then the dot product, u dotted with v, is just going to be what we would say is the sum for the product of the corresponding components in each vector. It is going to be the component u1 times the component v1, right? Added to the component u2 times the component v2, all right? It is going to be the sum for the product of the corresponding components in each vector. That is how we're going to calculate the dot product using this theorem in 2-dimensional space, and also describes how we're going to calculate that dot product in 3-dimensional space. And this continues on up into the nth dimension, right? If u bar is given by the vector u1 comma u2 comma u3, and v bar is given by the vector v1 comma v2 comma v3 in our 3-dimensional space, right? Then the dot product of u times v will be u1 times v1 plus u2 times v2 plus u3 times v3, right? It will be the sum for the products of these corresponding components from our two vectors, right? This is going to be the method we use to calculate those cross products. Cross products, not cross products, dot products, right? If we consider an example, right, we might consider u and v here in 3-dimensional space. If u is given by 4, 1, 8, and v is described by 5, -2, 0, the dot product of u with v is simply going to be u times 5, which is 20, plus -1 times -2, which is 2, plus 8 times 0, which is 0. It's going to be 20 plus 2 plus 0, which equals 22 in value. Right? It is a rather elementary calculation here, folks, right? That does follow this pattern where you sum the product for the corresponding components in each vector. Now, with that dot product calculated, if we go back and take note on what are the magnitudes of vector u and v, right? Furthermore, taking note that the magnitude of u is 9 and the magnitude of v is the square root of 29, and that our dot product equals 22, from the definition of the dot product, we can use these calculations above to actually determine the angle measurement forming between these two vectors, to determine that smallest angle measurement that's forming between these two vectors, right? Since u dotted with v, which we know equals 22, is also just equivalent to the magnitude of u times the magnitude of v times the cosine of theta, that means that 22 must be equal to 9 root 29 times the cosine of theta, where if we solve this equation for theta, dividing both sides by 9 over root 29 and taking the arc cosine of both sides, we will find that angle measurement theta then is just the cosine inverse of 22 divided by 9 root 29. Where if you put that into your calculator, right, and calculate that out, making sure things are in degrees, you will get a degree measurement of about 63.0044 degrees. All right? So, folks, the dot product is a measurement that depends upon, it's a scalar value that depends upon the magnitudes of u and v and the angle measurement that forms between these two vectors. However, when we go about calculating it, we have two ways of calculating it. We could use the defined formula, or we could use the calculation presented in these theorems. And if we know the dot product for two vectors and we know the two vectors themselves, we can always use that dot product along with the definition of it to actually find the angle measurement between those two vectors, right? If those vectors were placed in the standard position, and we did that work here, right? Now, with dot product, there are a couple of useful properties we just take quick note of. First of all, that the dot product itself is what we call a commutative property. You can change the order of a dot product and it does not change its value. All right? U dotted with V is the same thing as V dotted with U. Right? If C is a constant multiple, is a scalar constant, a constant scalar multiple, and you multiply that across a dot product, that C will distribute itself to each of the vectors in that dot product, giving you the product of the constant, or the dot product for the constant multiple of each vector, which is what we see here. And then likewise, a dot product operator will distribute itself across a summation of two vectors, where the dot product for the summation of two vectors is really just the sum of the dot product between what we might say the vector, well, if it would be the dot product's summation, we might say here, right? Or the sum of the dot product with that multiple, that vector u in the dot product being distributed across this summation, right? Those are just some quick properties of how dot products behave in those arrangements. All right. They can also be used to calculate what we call projections of one vector onto another, right? Where if we're talking about vector u and vector v, we might be thinking about what we call the orthogonal projection of u onto v, which is itself just a vector describing how much of vector u is in the direction of vector v, right? And that's what we see here in this illustration. In this illustration here, we have our two-dimensional system, and we have these vectors u and v in standard position, right? How much of vector u is in the direction of v, we might say here, when in a standard position. Right? Where here, what we mean by that is if we think about vector u here being this vector and vector v being this vector, sum of vector u is actually happening in the direction of vector v, and sum of vector u is not happening in the direction of vector v. How much of u is happening in the direction of vector v, right, is what we call the projection of u onto v. And what this actually highlights here is another vector that actually points in the direction of v, whose length is dependent upon the length and position of u, right? U is being, in a sense, projected over here onto vector v, whereas it's projected onto v, this projection is actually happening at a right angle to v. Right? That's why it's referred to as an orthogonal projection. And what this tells us is how much of vector u is moving here in the direction of v. Whereas how much of u is not moving in the direction of v, well, that's actually what would be described by this dotted line from v to u. Right? And what we would note is the amount projected in the direction of v added to the amount not projected into the direction of v would actually produce your vector u in its description. Now, as for how do we calculate this vector, this projection of u onto v, we say, right? That's given below here, and it does involve the dot product, right? Note the orthogonal projection of u onto v is actually denoted this way, right? You're going to project onto v this vector u. You're going to apply to vector u this projection onto v, right? And what it is given by is this scalar value, the dot product of u with v divided by v's magnitude. And notice the order of these is important. U is projecting onto v. That is different than v projecting onto u, where the order of this projection would reverse. You'd have the little subscript be u, and you'd apply it to vector v, where in this formula u and v would reverse their orientation. But here for u on the v, it is the scalar given by u dot v divided by the magnitude of v, the vector you're projecting onto, times vector v divided by its magnitude, where you will notice vector v divided by its magnitude is just a scalar, well, I should be careful there, is a unit vector in the direction of v, right? We're going to, in a sense, take the unit vector in the direction of v and scale it by the dot product divided by the magnitude of v, right? Now, one thing you would note is if v is your itself a unit vector, then it really is just the dot product is nothing more than a scalar multiple of the unit vector in the direction of v that is describing how much u is happening in the direction of v, right? So, all right, it is the scalar multiple, u dot v divided by the magnitude of v. Those are both scalar values in the scalar division, times by this vector description. This second factor is a vector description describing a unit vector in the direction of v, right? If we consider a specific case, let's calculate this projection. Right? We might consider the orthogonal projection of the vector u 3, 1, 1 onto the vector v 0, 3, 4. In this case, we can notice, right, u dotted with v, let me bring back that case into view, right? U dotted with v, again, is just going to be 3 times 0 plus 1 times 3 plus 1 times 4, right? Well, that's going to be 0 plus 3 plus 4, 7 in value. And in the orthogonal projection of the vector u onto v, you're going to need the magnitude of v, where the magnitude of v is just the square root of 3 squared plus 4 squared plus 0 squared. There would be a plus 0 inside there for the plus 0 squared. We don't see it. And that is the square root of 25, which does equal 5 in value. All right. So the projection of u onto v would be the scalar value 7/5 arranged by taking 7, the dot product of u and v, over the magnitude of v, and multiplying that by this vector description, the vector v, right, divided by its length, which is going to make this into a unit vector. Now, if we just distribute this is 7/5 times a fifth, that's 7/25. And if 7/25 distributes itself to these three components, it would be 7/25 times 0 is 0, 7/25 times 3 is 21/25, and 7/25 times 4 is going to produce 28/25. And this becomes what we call the projection of u onto v. This is the vector that's describing how much of vector u happens in the direction of vector v. All right? It is that projection vector. All right? So dot products can be used to calculate these projections. And along with that, the dot product can also be used to calculate the work done moving an object with a force described by some force vector over a distance and direction described by some what we would call just direction vector, right? The work done given by the following, well, the work done would actually be then given by the following calculation, where that work is nothing more than just the dot product of force with distance, all right? In the one-dimensional realm, we should be familiar with the idea that work done in a one-dimensional system, right? Moving a force in one dimension, or applying a force in one dimension, a given distance is really just force times distance. Well, here, if we move into the n-dimensional realm where that force now becomes a vector description in n-dimensional space, and that distance becomes some distance vector describing distance and direction in n-dimensional space, then work is really just the dot product now of force, that force vector with that distance or direction vector. All right. If we look at a quick example of this calculation, right, we might consider the work done, right, by a force measuring the square root of 10 newtons in the direction of this unit vector, 3 over the root 10 comma 1 over the root 10, right? Moving an object this distance, 20 meters, up a ramp where that ramp forms a 30-degree incline with the horizontal. All right? In this case, your force vector would be just that force, square root of 10 times the direction, right? Which would produce the vector 3 comma 1. And your direction vector D would just be the distance traveled 20 times the unit vector describing the direction up a ramp that forms a 30-degree angle with the incline. And where you're going to get that description of a unit vector from is this angle measurement 30 degrees within the unit circle, right? The x-coordinate would come from the cosine of 30 degrees and the y-coordinate from the sine of 30 degrees. Well, that direction inside the unit circle is going to be the unit vector description seen here in this description of the incline, right? Where if we take 20 times those measurements, now cosine 30 is square root of 3 over 2, so that would turn into 10 root 3, simplifying the 2 with the 20. And the sine of 30 is 1/2, so 20 times 1/2 would just become 10. Now, as for the work done, it is just the dot product of 3 comma 1 with the vector 10 root 3 comma 10. So that would be 30 root 3 comma 10. Well, I should say plus 10, not comma 10. It's a scalar. All right. And if we take note, that is the work that we obtain here. If we're measuring in newtons and distance is measured in meters, then we are obtaining work in a description of Newton meters. And it is 3 times 10 root 30, right, plus 1 times 10, which is just 10. So we get 30 root 3 plus 10 as our work description here. All right? So, folks, this is the vector operation known as a dot product. It has a couple of applications here in the calculation of work, in the calculation of projection vectors, right? In the determining of the angle between two vectors, right? You can all use this dot product operation. And the dot product operation does have a calculation, right, that we rely on, seen here in this theorem for both 2- and 3-dimensional vectors, and that does extend up into n-dimensional space. And it has an understanding, a definition, right, that relates itself to that angle measurement between these two vectors in standard position, right? It is an example of a product that we can calculate with two vectors where the value of that product is a scalar value. So we call this the scalar product, right, of two vectors, right? So that is the first of these products. We're going to come back to the case for a vector product, a product of two vectors that produces another vector, which is going to be the case for what we call a cross product, right, folks? So that is my next video. I will have that up here shortly. I will see you all then.